Okay, welcome back. So today we will continue with our physics tutorial. Okay, subtopic 13.1.3e, deduce the change in the potential energy delta U between the 2 points in the electric field. So consider there is a positive point charge. Okay, so this is a positive point charge Q. Okay, held stationary at O exert a repulsive force on a positive test charge. Okay, so if this is a point charge, okay, so this is our point charge and this is our test charge. Okay, so what happened point charge and test charge is because positive and positive, so it will experience a repulsive force. Okay, it will experience a repulsive force. Okay, so A and B are 2 points on the line that passes through O and P. So there's a 2 point here. So the test charge at point P is moved by an external force through a small distance. Okay, so if let's say we want to bring this test charge from B to point A. Okay, so we need to do external force. Why we need to do external force? Because positive and positive initially, naturally, when we put together, it will experience a repulsive force. So when we want to move this test charge from B to A, meaning that we are moving this test charge to the left. So we need to do work because if let's say we are not doing work, this test charge will move to the right. Okay, so if let's say you want to bring it from B to A, you need to do some work to bring. That's why it call it external force through a small distance of delta R. Okay, so this is our delta R. Okay, so delta R is so small that the force can be considered to be constant. Thus, the work done by the external force, so we give it as, okay, we know that work done equals to Fs, okay, or Fd, okay, cos theta. So we can write as dW, the work done, equals to negative F dr. Okay, so after that, you will get the equation. Finally, you will get the equations. Work done equals to K, Q is the point charge, Q naught is the test charge, 1 over RA minus 1 over RB. Okay, and we can also write as work done equals to UA minus UB. Why is equals to UA minus UB? Because U equals to K, Q, Q over R. Okay, so if let's say we want to write KQ, Q naught over RA, so we can write as UA minus UB. Or we can write as delta UAB because it's A minus B. So we write AB. Okay, AB. Okay, next. We goes to D. Okay, if RB is infinity and RA, the distance is R, then the work done in bringing the test charge from infinity to A is equals to this. Okay, so for example, let's say this is a positive charge. Okay. Okay, if let's say this is a point, this is a radius R, and we label this one as point A. Okay, and then this is, for example, let's say this is R equals to infinity. So when R equals to infinity, your potential, electric potential is equals to 0 because it's too far. Okay, and the electric potential is reducing. So when you reach infinity, your V will equals to 0. Okay, so if let's say you want to bring a test charge, you want to bring a test charge from infinity. Okay, from infinity to point A, meaning that you need to bring this Q naught. This is the point charge. So this one is capital. You want to bring it from infinity to point A. Okay, what should you do? So our work is infinity to A. So we write as V final minus V initial times the test charge, which is Q naught. So your V final is your VA, and your V initial is V infinity, and your V infinity is equals to 0. So that's why our equation is VA times our test charge. Or we can write it as, okay, we can write it as, okay, so we can write it as KQ over R times Q naught. Okay, so actually this one we can also write as our change of potential energy. Okay, so we can write as V work done infinity to A, we can write it as electric potential energy, or we can write it as KQ Q naught over R. Okay, so since VBA equals to work done A to B, okay, work done A to B, meaning that is VB, my final minus V initial. Okay, or we can write as delta V equals to work done over test charge. So finally, our change of electric potential energy, we can write it as is actually equals to work done is equals to change of delta VQ, or we can write it as V final minus V initial times test charge. Okay, so this is change of potential energy. So potential energy actually is our work done. Okay, it's actually work done. Okay, if the value for work done is positive, so our work done or change of delta U or change V final minus U initial, or we can write as delta VQ, or we can write as V final minus V initial times test charge. Okay, so if let's say it is negative, meaning that the work done by the system, okay, by the system, meaning that system will do work automatically. If the work done you get is positive, meaning that work done on the system, on the system, okay, on the system, meaning that you need to do work on the system. Okay, you need to do some work on the system. Okay, so for example, okay, let's say this is our, okay, let's say this is a positive point charge, and this is your VA is equals to, for example, because this point charge is positive, so it's positive 10 volt. And also, let's say here we have VB, so positive 8 volt. So if let's say you want to find work done, okay, you want to find work done from to bring a test charge from point B to point A. So if let's say this is a test charge, positive, automatically actually it will move to the right. But if let's say you want to find work done B to A, meaning that you want to bring test charge from B to A, so we must write B to A, meaning is V final, meaning is VA minus VB over Q. Okay, so your VA is equals to positive 10 minus 8 volt, and the test charge is Q. Okay, so you will get a positive 2Q. Okay, you will get a positive 2Q. So positive here meaning that you need to do work, okay, on the system. On the system. Okay, if let's say this is a positive point charge and this is your VA equals to positive 10 volt. This is your VB equals to positive 8 volt. Okay, if let's say you want to, this is a test charge. So automatically positive point charge, positive test charge, your test charge will move to the right. Okay, and coincident, if let's say you want to bring your test charge from A to B, just now is from B to A. Okay, so we actually don't need to do work because when we put positive and positive, your positive test charge will automatically move to the right. Okay, so your work done from A to B, so we will take V final is B minus VA times the test charge. Okay, So your VA is equals to 10 minus 8. Okay, so you will get positive 2Q. Okay, positive 2Q meaning that your work done, okay, your work done, you will get, it's actually 8 minus 10. It's actually 8 minus 10. Okay, so here you will get a negative value. Okay, you will get a negative value. Okay, so here is 8 minus 10, so you will get negative 2Q. Negative here indicate that your work done by the system. Okay, by the system. So by the system meaning that you don't need to do work. When you put a test charge here, automatically it will move from A to B. Automatically it will move by the system. So you don't need to do any extra work. Okay. Okay, next one is, okay, we go to the example. Okay, we go to the example. Example number 11. Okay, example number 11. A negative test charge. Okay, so this is a negative Q naught is a negative 0.75 millicoulomb. Because it's mentioned negative test charge traveling from X to Y. Okay, from X to Y in the electric field. Experience a potential drop. So your delta V is negative 200 volt because drop, because of the word drop. So determine the potential at Y if a potential 20 volt exit at point X. Okay. So here I need to okay, we write here delta V, okay, is equals to Vy minus Vx and is equals to negative 200 volt. Okay, so your Vy will equal minus positive 20, okay, equals to negative 200 volt. So meaning that your Vy is equals to negative 180 volt. Okay, so this is the first answer for A. Okay, because the question says it's between point X and also point Y. Okay. Okay, determine the work done in this charge transfer. Is this work on or by the system? Okay. So because the question says from X to Y. Okay, from X to Y. So our work done is from X to Y. Okay, equals to V final minus V initial times the test charge. Okay, so V final, because it's X to Y, so it's Vy minus Vx. Okay, and times the test charge that you bring. Okay, so your Vy is negative 180. Okay, Vx is positive 20. So actually, we don't need to write one by one because we know that delta V is equals to negative 200. Okay, from the just now, the value that we get. Okay, but if you want to write also can, times your test charge. So your test charge just now is negative 0.75 times 10 to the power of negative 3. Okay, so for electric potential or electric potential energy is a scalar quantity, meaning that you need to consider, you need to substitute in all the sign convention, positive, negative, okay, because it's a scalar quantity. So finally, you will get your work done is equals to, okay, is equals to positive 0.15 joule. Okay, so positive meaning that you need to do work on the system. Okay, you need to do work. Okay, you need to do work on the system. Okay, so this is work done on the system or on the field. Okay, or on the field. Okay, next, determine the potential energy. Potential energy equation is KQ over R. Or we can write it as V times our test charge. Okay, times our test charge. So if let's say the first one you want to find electric potential energy on X. Okay, so this one is you must substitute Vx. So Vx is positive 20 and the test charge that we bring is negative 0.75, negative 3. Okay, so you will get a negative 0.015 joule. Okay, so this is potential energy for X. Okay, potential energy for Y, similar, also KQQ over R, or we can write as VYQ naught. Okay, so Vy just now we get is negative 180 and Q is negative 0.75 times 10 to the power negative 3. So finally, we will get positive 0.135 joule. Okay, so that's all for example 11. Okay, so you may pause the video if let's say you're still calculating. Okay, so final 13.f, 1.3f, sorry, 1.3f, calculate a potential energy. Okay, so this one, potential energy is for the system. Okay, if the question mentioned of a system. So if let's say for a system, okay, you must include all the possibility for the charges. Okay, so the electric potential energy of the Earth system, okay, you must refer of a system of a point charge is defined as the work require assembly. Assembly must meaning that total up, okay, of the charge by bringing them close together. As the system from an infinite distance where it's the electric potential generated by the charges. So let's say we have 3 charges, meaning that we have 3 electric potential energy for this system. Okay, for the whole system. Okay, so this one is okay, we make friends. Okay, 1 and 2 we have U12. Okay, 2 and 3 we also can make friend. So we have U23. Okay, 1 and 3 also we can make friend. Okay, so total up we have U12, U23, U13. So we can write as U12, U23, and also U13. Okay, so we can write as U equals to K Q1 Q2 over R plus K Q2 Q3 over R plus K Q1 Q3 over R. Okay, so of course R is between them. Okay, so this is 1, 2. This is between them is 2, 3. Between them is 1, 3. Okay, so this is the equations. If let's say the question ask you to find the electric potential energy for the whole system, so you total out, you find all the possibility between the charges. Okay, so we add on. Okay, we assembly all the electric potential. We add total up everything. Okay, we try example number 12. So there's only 2 point charges. One is Q1, another one Q2 are placed 4 and 5 meter. Okay, so the first one, calculate the electric potential at point P. So when you want to find E, remember always you put a positive test charge. You assume there is a positive test charge. So negative, positive, you will attract. So we label it as E2. Positive and also positive. So it is E2. Okay. Oh, sorry. This is not electric. This is electric potential. Okay, sorry, this is electric potential. So if let's say electric field, let's say electric field, you write E. But the question say electric potential. Okay, electric potential, we want to find V. Okay, we want to find V. So when you want to find V, it's easy. Okay, you just put that here, our superstar. So it's influenced by Q1 and it's influenced by Q2. So you just total up. V total equals to V1 plus V2. Okay, so Q1 over R plus Q2 over R. So you just substitute. K is, you can factorize out. Q1 is a positive. So when we say positive, you must substitute positive 2 micro. Distance is 4 meter. Okay, plus Q2. Q2 is negative. Okay, it's negative. So you must substitute negative because it's a scalar quantity. And the distance is 5. Okay, so you calculate. And you will find out that the answer is a negative 6,300 volt. Okay, it's a 6,300 volt. Okay, so next one. If a test charge, so now we put a test charge, 3 microcoulomb move from infinity to point P. Okay, so meaning that you want to bring a test charge from infinity to point P. Okay, so work done. Determine the change in electric potential energy. So change of electric potential energy actually is our work done. Okay, to bring from infinity to point P. So we must write VP final minus initial over the test charge. So VP just now we get is negative 6,300 and V infinity is 0. And test charge is positive 3 micro. Okay, so you will get negative 1.89 times 10 to the power negative 2 joule. Okay, so actually change in the electric potential energy is our work done. So we are finding the work done from infinity to point P. Okay, and point P actually is influenced by 2 point charges. Okay, it's influenced by 2 point charges. Okay, and last one, C. When the charge Q3 at point P, calculate the electric potential energy for the system of the charge. So meaning that now you want to find the electric potential energy for the whole system. Okay, if let's say here we already have negative, positive, and also our test charge also positive. Okay, so let's say this is your Q1, Q2, and also Q3. So we have 3 electric potential. Okay, U12, U23, U13. So you just total up. Okay, so this one will be your homework. Okay, 213 plus U23. Okay, so you find out what is the answer. Okay, what is the answer? Okay, so this one, C, is your homework. Okay, so you just total up everything, including the sign. If let's say negative, you must substitute in the negative. Okay, if let's say positive, you must substitute in the positive. Okay, so that's all for today. We will continue in the next video.